Modern robots process a staggering amount of information. Every second, hundreds of sensors, cameras, lasers, accelerometers are generating a constant crashing wave of raw data. If your machine behaves unexpectedly in the field, figuring out exactly what went wrong is incredibly difficult when you have to sift through gigabytes of pure numerical noise. Trying to find just one split-second sensor failure in that mess feels like searching for a single grain of sand in a blizzard. We are going to solve this by capturing the data exactly as it happens using a tool called rosbag and then running it through a custom Python script. This process will extract only the exact sensor readings we actually want to analyze, leaving the rest of the noise behind. Before we start, make sure your environment is ready. You need a working installation of ROS and Python on your system, and you need an active Catkin workspace configured and sourced in your terminal. Organizing this flood of raw information is the first necessary step to actually diagnosing and controlling complex mechanical systems. Let's move over to the command line. Step 1 is always sourcing your workspace. If you forget to run the setup.bash file, your terminal won't recognize any ROS commands, and you'll get hit with immediate errors. On screen, you can see a split view of our robot in motion and the terminal we're using to record its sensors. To capture data from the robot's GPS and IMU simultaneously, we use the command rosbag record-o myrobotdata.bag, followed by /GPS and /IMU. That -o flag simply tells the system to output the captured data into a specific file, which we are choosing to name myrobotdata.bag. When you finish your test run, safely kill the process in the terminal using Ctrl-C. The system will finalize and save the .bag file right there in your current directory. We can verify this capture by replaying it. As shown in this new terminal window, executing rosbag play lets us watch the data stream back out. We've added a -r 0.5 flag, and you can see the playback timer counting up. That -r 0.5 modifier forces the replay at half speed. When you're dealing with hundreds of sensor updates a second, slowing the data down gives you a realistic chance to spot fast-moving anomalies. The chaotic, unpredictable physical test run is now safely contained on your hard drive, ready to be reviewed as many times as you need. Now we have a massive file full of every single reading from both sensors. To isolate only the moments when the robot tilted sharply, we need to switch over to a code editor and build a custom filter. Looking at our code editor, we start off by importing the rosbag library. Then we assign a variable to open our massive myrobotdata.bag file in read mode. Next, we use a standard Python with statement to create and open a new file named filtered.bag in write mode. Doing it this way ensures the system automatically closes the file when the script finishes, preventing corruption. We follow that up by writing a loop for topic, message, and time in bag.read messages. This instructs the script to scan through every single packet of data in the original file chronologically. Inside that loop, we write our specific condition. We tell it to look exclusively for data where the topic matches /IMU and the x-axis orientation value is greater than 0.5. When the script finds a data packet that meets both of these strict criteria, it writes it directly into our new, clean output file. Pay close attention here. The topic names in your Python script must identically match the names you typed into the terminal during the recording phase, or your output file will be completely empty. With just a few lines of logic, we've built a highly targeted analytical tool capable of sifting through massive amounts of raw observation. The last step is execution. You'll run this Python script directly from your terminal. Make sure you navigate to the exact folder where your original bag file is stored. If the script can't find the source file in its current directory, it will fail to run. Looking at the terminal's file directory after the script finishes, you can see the result. There is our massive original myrobot data file sitting right next to our new filtered.bag, which is a fraction of the size. We've effectively distilled gigabytes of mechanical noise down into just a few kilobytes of relevant, actionable signal. We started with a chaotic stream of continuous movement data, captured it in real time, and programmatically isolated the precise moments the robot's IMU tilted past our threshold. You can now use this refined file to run highly focused, distraction-free simulations, or hand it off to a data science team for deep analysis without forcing them to sort through irrelevant numbers. And if you want to scale this workflow up, just replace the individual topic names with the -A flag in the initial recording step. That single flag will capture data from every available sensor on the robot simultaneously. Recording raw data is useful, but being able to filter and manipulate it at will gives you total authority over the information your mechanical systems produce.